Cool. So I want to go back to a question that you probably saw in a first course linear algebra, and that's a question of when can you diagonalize a matrix? That is, if you're given some matrix A, when can we write A as some change of basis into some diagonal matrix D, right? So this is some change of basis matrix P. This is a diagonal matrix D. So when can you do this? Well, in a lot of ways, the decompositions we've been looking at in this class have been trying to get at this question in some sense. One is if you have an arbitrary matrix, you can always write that arbitrary matrix A as some unitary matrix times an upper triangular matrix times the inverse of the unitary matrix, right? The inverse of a unitary matrix is its complex conjugate, conjugate transpose, sorry. And so this is sure triangulation. It's like, that's nice, these are unitary matrices, but this is not necessarily diagonal, right? So that's not necessarily diagonal. We always can get a diagonal matrix if for any matrix, under our singular value decomposition. So that's when we write it of this form. But now U and V are not necessarily the same matrix, right? They're not necessarily the same basis. U is some unitary matrix. V is the inverse or the conjugate transpose of some other unitary matrix. So it's like those are kind of have this vibe, but neither one really gives you, in general, a diagonal matrix. And that's because in general you can't, right? If you're given some arbitrary matrix A, you're not always able to diagonalize A. So maybe if you think back to your first course linear algebra, you're given some conditions about, a matrix is diagonalizable if and only if, and you have these kinds of conditions. I want to remind you of that with an example. So I want to show you an example of where diagonalization might fail and try and help you remember what's all going on there and why it fails. And then we're going to say, well, is there some way to patch this up to do our best to diagonalize a matrix? Maybe it won't be exactly diagonal, but maybe we can get pretty close. So the matrix A I want us to think about is this guy. So I want to open with a really concrete example. I did this out last night, so here's the matrix. Okay, so we want to know if this is diagonalizable. And so one first thing we can do is calculate the eigenvalues of this matrix. And so we find the eigenvalues by looking at the characteristic polynomial, which is defined to be just the determinant of A minus lambda times their density. And if you calculate that, it comes out to be negative lambda minus 2 squared times lambda minus 1. So you can calculate that out and then factor it, and this is what you get. And so then if we look, we want to ask, well, when is this equal to 0? That's going to give us the eigenvalues. We recover that our eigenvalues are 1 and 2, right? Although the fact this is squared means that we could record the data that this 1 has an algebraic multiplicity of 1, and this 2 has an algebraic multiplicity of 2. Essentially, 2 is showing up twice as an eigenvalue, whereas 1 only shows up once as an eigenvalue. Okay, so now that maybe I remind you of this word algebraic multiplicity, do you remember the criteria for when a matrix is diagonalizable? There's something to do with this. No, so not quite. It's going to be when your geometric multiplicity equals your algebraic multiplicity. So let me remind you what I mean by geometric multiplicity. So if I look at the eigenvalue lambda equals 1, I think this is something you probably saw in like an introduction to linear algebra course. If you look at the eigenvalue lambda equals 1, we can look at this matrix A equals 1 minus I. So where is this coming from? Well, we're interested in when is A equal to lambda I, right? And so in particular, we're trying to solve when is A times a vector V equal to your eigenvalue times the vector V, right? And you're like, well, that's going to be true when a minus lambda I times v is 0, right? Just factor out my v on this side. And so what I'm really interested in to find my eigenvalues is I'm trying to find all of the vectors that you multiply this matrix by to get 0. And those vectors are called vectors in the null space. V, we'd say, is in the null space of A minus lambda I. So if you want to calculate the null space, for example, for lambda equals 1, our matrix is just becoming 0, minus 1, 2, minus 1, minus 2, 4, minus 1, minus 2, 4. So you're trying to calculate this null space. That is, we're trying to find vectors v, vectors of the form, say, x, y, z. So this comes out to be 0, 0, 0. Right. So you might look at this, and does anyone see like a solution for what x, y, z could be? What's one possible solution for x, y, z?
0, 2, 1.
Great. One solution for v is you could set your v to be 0, 2, and 1. It's like plug that in. That gives you the first row vanishes. The second row you get 2 times this and 1 times this. And notice the second guy is always negative twice the first. The third guy is negative twice the second. So that's always going to work. So that's great. Are there other guys? Well, yeah, you can scale this by whatever you want. You could have done 0, 4, 2 or 0, 6, 3. That would have also worked, right? But then you're like, well, is there anything else that's linearly independent from this v? Or is this is it only just scalar multiples of this guy? And that's now asking a different question. You're now asking, what is the dimension of the null space? And that's what we call nullity. The nullity of some vector is just asking me for the dimension of the null space. How many linearly independent vectors are there that are in this null space? How do you find that? Well, one way you can find it is by remembering that the nullity is preserved under row operations. So you can row reduce this matrix. You can have some matrix like 0, minus 1, 2, minus 1, minus 2, 4, minus 1, minus 2, 4, and you just row reduce him. And so you're like, oh, these bottom two guys are the same. So if you subtract a copy from the second row from the last row, you get 0 on the bottom now. So now I'm going to get all zeros on the bottom. And then you're like, oh, wait, this guy is like 2 copies of the row under him. Like if I subtract 2 copies of the first row from the second, my negative 1 remains negative 1, but minus 2 copies of this gives me a 0, and 4 minus 2 copies of 2 gives me a 0. And then on top, I still have 0, minus 1, 2. So it's like, OK, the nullity of this matrix is the same as the nullity of this matrix. That is, the dimension of this null space is the same as the dimension of this null space. This is just row reduction. And then you can simplify things a little bit more if you want. If you want to like multiply this by a negative 1, you could. If you want to multiply that by negative 1, you might. But then it's just like sit down and think. Like, what is the nullity of this? If this is times by x, y, z to give you 0, what does that mean? Like, what has to be true of x, y, and z for this to come out to be 0? And you're like, well, this second, multiplying the second row tells you x has to be 0. And then multiplying the first row tells you that your y equals 2z. And then your last row doesn't give you any constraints. You just have 0, 0. But you're like, well, then how many degrees of freedom do you really have? X is locked in. It has to be 0. Y is determined by whatever z is. And so the moment you determine z, you also determine x and y. Right? So this is saying that this null space is just guys of the form 0, 2, 1. Linear multiples of this, scalar multiples of 0, 2, 1. So multiples of 0, 2, 1. Now, that is not going to be the same as, well, okay, this is exactly the same as what we just had. But the point is, all I'm interested in here is just the dimension. This is dimension 1. It's just multiples of a single vector. And so the nullity is 1. Okay, great. There's my nullity, the dimension of this null space. And what I want to highlight is this nullity, for 1, was the same as my algebraic multiplicity. So your nullity is sometimes called your geometric multiplicity for your eigenvalue, for the eigenvalue lambda equals 1. And in this case, my geometric multiplicity came out to equal my algebraic multiplicity. Does this seem vaguely familiar at all? Did you guys do a little bit of this in your last course? Okay. Well, now let's investigate the case of my second eigenvalue of lambda equals 2. At lambda equals 2, I'm now going to be looking at my matrix A minus 2 identity. So that's going to give me the matrix minus 1. This second row, I get a minus 3 in the center. Everything else is the same. And then the last row, the bottom right value moves from 5 to 3, subtracting 2 times the identity. Okay, so let's play the same game, right? It's like ultimately at the end of the game, at the end of the day, I'm going to want to know like what are the full set of solutions to this, or what is the dimension of the space that contains all vectors that give me this. It's like maybe by looking at it, you can just see one such vector already. Like, can you see one? Ah, that 2 is positive. Maybe now you can see one. 1, 1, 1, right? So like one example of a vector that would be in your null space would be 1, 1, 1. That's one such example that's in your null space of A minus 2i. But there are other ones, 2, 2, 2, 3, 3, 3. Okay, so all scalar copies of this. Is there another one in there? Something linearly independent from 1, 1, 1? Well, let's check. Let's try and calculate the nullity of this guy. So I'm interested in calculating what is the nullity, what is the dimension of the null space of A minus 2i. And so to do that, I'm just going to do row operations on this matrix. And you're like, well, check it. This second matrix is just the sum of the first and the last. So lots of ways you can play around with this. One way is, oh, no, that's not quite true, is it? No, it's not the sum. This guy and this guy's the sum. Oh, no, he's not even close to the sum. Okay, so that was a lie. Let's just start subtracting rows from each other and see what happens. Let's subtract the last row from the second row. So he's now going to be 0, minus 1, 1. Let's subtract the first row from the last row. He's now going to be 0, minus 1, 1, and minus 1, minus 1, 2. And then you're like, okay, well, that bottom row is now a duplicate of the guy above him. So if you subtract him from the guy above him, you get 0, 0. And then you can subtract the second row from the top row. So minus 1 minus minus 1 is 0, and 2 minus 1 is 1. Well, this is looking pretty good. So like, what's the nullity of this guy? Huh? Yeah, it's 1 just like before. If you want to like and convince yourself, you're like, okay, if I have x, y, z, and I want to know when it comes out to be 0, 0, 0, this first guy introduced the constraint that my x must equal my z. But then this condition gives you that y is also equal to z. And so your x, y, and z must all be equal to each other. And so you only have 1 degree of freedom. And so your nullity has dimension 1. It's just all scalar copies of 1, 1, 1, right? Okay. Cool. So my geometric multiplicity for the eigenvalue 2 is 1. Uh-oh. My algebraic multiplicity was 2. It's not a problem. It turns out in general, I mean, this is something you proved in your last course, if you think back, that your geometric multiplicity is always less than or equal to your algebraic multiplicity. But it also turns out that you're able to diagonalize if and only if your geometric multiplicities equal your algebraic multiplicities. And it's because we came up short here that we're not able to diagonalize this matrix. Right? So there's no way to diagonalize this. Not even over the complex numbers. You might be like, is it just because, sometimes you have real matrices and the eigenvalues are complex, but it's like even over the complex numbers, you can't diagonalize this. So we cannot write A as some P inverse. So our goal for today is we want to start asking the question, we're going to be spending this week talking about this. Well, is there some way that given any square matrix A, so given any square matrix, let's say we'll do it in general of the complex numbers, that we can write A as P times something almost diagonal times P inverse. So can we do a change of basis, not to a diagonal matrix, we just said we couldn't, but to something almost diagonal? And yes, we can. Right? This is what we're going to do. This is our last. So this is going to be our last decomposition result we're going to see in this class. The last way of representing A, as for any square matrix A, can be written as, well, a special form that we're about to talk about. So first, let me use some terminology. We're going to be talking about Jordan blocks. So we're building up to a Jordan decomposition. And here's the idea of a Jordan block. A Jordan block is a matrix that has some entry along the diagonal. I don't know what it is. I'll call it lambda. So lambda, 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 however many you have. And then you have ones on the superdiagonal, on the diagonal above the diagonal, and zeros everywhere else. So this would be an example of a 3 by 3 Jordan block with diagonal value lambda. Some Jordan blocks are very simple. You can have a 1 by 1 Jordan block with some value like 3. That's just going to be the matrix with just 3, right? If you want to have, let's say, a 2 by 2 Jordan block with the value, I don't know, 7, that's just going to look like 7's here and a 1 above it. And if you want to have, I don't know, something more complicated like a 4 by 4 Jordan block with some number like -1, that's going to look like 4 copies of -1 and 1's above them. Yeah? Get the idea of a Jordan block? Okay. So these are Jordan blocks. We can also have matrices that are built up out of several Jordan blocks. So for example, I might have a matrix that has a 2 by 2 Jordan block with diagonal value 0. And then another matrix that has, I don't know, let's say a 3 by 3 Jordan block with diagonal value 2. So what is that going to look like? Well, overall, it's going to be a 5 by 5 matrix. These zeros represent matrices, so this is a 2 by 3 and 3 by 2 matrices. But we're going to end up here with, this guy is going to be zeros along the diagonal, a 1 on top. So here's my first Jordan block corresponding to this guy. And then I want a Jordan block here, a 3 by 3 Jordan block with 2's on the diagonal. So here's my 2x2 Jordan block, 3x3 Jordan block corresponding to this guy, and then zeros everywhere else. Okay, are we happy with the notation so far? So this matrix is not a diagonal matrix, right? It's got some extra stuff, some extra ones. But it's almost diagonal. It's going to turn out this is exactly what we need to satisfy our condition. So here's the big theorem. We're not going to prove it today. We'll make a little bit of progress towards it. We'll focus on the proof next class and then some applications on Friday. Today I'm trying to introduce it, and we'll talk a little bit about how to work with it. So here's our theorem. We can write any matrix, any square matrix, as A equals Pj P inverse, where J is just some almost diagonal matrix made up of these Jordan blocks, like this guy. So I don't know how big these Jordan blocks are. I'll say K1, so it's a K1 by K1 matrix with some value lambda 1. I'll call this K2 with some value lambda 2, down through whatever the last one is. Let's say Km with some value lambda m. And zeros everywhere else, right? Zeros everywhere else. This matrix, this J, is called the Jordan canonical form. And my goal by the end of today's class is to try and convince you that J is unique up to reordering of the Jordan blocks. So for instance, these two could have been switched. So there are two parts to this theorem. One is the existence, that A can be written as up to some change of basis in this Jordan canonical form. And the second is the uniqueness, right? So I'll build up to talking a little bit about uniqueness by the end of today's class, but then we need to come back in our next class and talk more about the existence, why you can always do this, right? Okay. I'll come back to this example in a few minutes. So let's just remind ourselves what we already found. Although this guy had algebraic multiplicity 1 and 2, we said here that his geometric multiplicity was 1 for both of them. So those both have geometric multiplicity 1. Okay, so maybe I should just like pause for a second. Are there any questions about what this theorem is saying? If not, yeah. P is just change of basis. It's not necessarily unitary. So it's just any invertible matrix, right? We're not guaranteed it's a nice unitary matrix. It's just some square matrix that's invertible, non-zero determinant, so that it has an inverse, right? So you just change in basis from your standard basis to some other basis. And it may no longer be an orthogonal basis, may no longer be orthonormal, right? You could have whatever the other basis be, you know, maybe something like that, right? P is just finding some basis so that the linear operation represented by A is under this new basis, now represented by this matrix.
So is there only one P
Well,
Is J dependent on?
yeah, so reordering the value, reordering these blocks would be like reordering the columns of P, right? And then of course, you can do things like if you scale 1P, if you scale it by 2, you're scaling the inverse by 1 over 2. And so that wouldn't change anything. So you'll be able to, P has a little bit of some freedom where you could scale it, or you can reorder the columns of P to reorder these blocks. But I guess what I really want to do is actually find what the Jordan canonical form corresponding to A is. And so my first observation is going to be, well, what are the eigenvalues of J? Why? Good. Since it's an upper triangular matrix, it's not quite diagonal, there's extra ones on top. But we've said before, upper triangular matrices, the eigenvalues are just the diagonal entries. So my eigenvalues of J, so this J has eigenvalues lambda 1, lambda 2 through lambda m. I mean, it was kind of suggestive when I started using lambdas that we're talking about eigenvalues. But since it's upper triangular, those really are the eigenvalues of J. But wait a second. What happens when you change base? Well, I mean, let's just prove this really fast. I mean, maybe you forgot this, but change of basis preserves eigenvalues. So let's do it over here. So like I want to argue that A and J have the same eigenvalue, right? So I know that like J times some V1 is lambda 1 times V1. Lambda 1 is some eigenvalue of J. I claim that it's also an eigenvalue of A. How can I see that? Change of basis. So change of basis preserves eigenvalues. So why is that? Well, here's why. I mean, we didn't even have to write it like this. We could have just done the original guy. So the claim is that, well, let's just see it here. That if you instead, if you change your basis, so if you want to change your basis, this is now A. But instead of looking at V1, I'm going to look at P of V1. So let's just write it like this. Let W1 be P of V1. Then I claim that, well, let's see. I mean, my claim is that A, which is your change of basis, W1 is lambda 1 W1. Okay, I didn't plan to do this, but this is what I want to show you. Why is that true? Well, the reason this is true is because from this relation, we get that J V1 is the same thing as J P inverse P V1, because these just cancel, which is the same thing as lambda I times V1. Now I'm going to multiply the left-hand side by a copy of P. So multiplying this by a copy of P, I can pull out lambda 1. And now what do you have? Well, this is exactly A. This is exactly W1 is lambda 1 times W1. So if lambda 1 is an eigenvalue for J, then lambda 1 is also an eigenvalue for A, where the corresponding eigenvector changes from V1 to P times V1. Your change of basis just changes the eigenvector. Is that good? So we're saying that A and J have the same eigenvalues. Lambda 1 through lambda m are eigenvalues for both A and J. So it's like, okay, so what can J look like? Well, I know J has to have eigenvalues 1 and 2. So what is the J corresponding to my A here? So given this A, what is J? Well, it has to have values 1 and 2. So you might look at this, and you'd be like, well, maybe it has like a 1 by 1 block for your 1, and a 2 by 2 block for your 2. So maybe my J looks something like this. Maybe it looks like a 1 by 1 block for my 1, and a 2 by 2 block for my 2. So maybe my J looks something like this, possibly. Or you're like, well, maybe the 1 has a 2 by 2 block, and the 2 has a 1 by 1 block. Like, that could be how it looks. So it could look like 1, 1, 1, and then a single 2. Or maybe it's like your 1 has a 1 by 1 block, your 2 has a 1 by 1 block, and then your 2 has another 1 by 1 block. This would be also something which is eigenvalues 1 and 2. This would be, well, then it actually comes out to be just diagonal. 1, 1, 2. I guess we rule this one out because we know it's not diagonal, right? But in principle, there's a lot of options is what I'm trying to show you, right? Like, I know it's one of these guys, but I don't know which one it is. So what I need is I need some way to count how many like J1 blocks are there of size 1 and how many of size 2, or like how many of the J2s are there of size 2 or of 1, right? Like, that's what I need to know is like, what combination of these should I have? Yep.
Maybe a 1, 2, 2.
Yeah, right. This one is 2 2s. You're right. I could have also had 1, 1, 2, but the way I wrote it was 1, 2, 2. We know that's not going to work, the last one, because we said this is not diagonalizable. But you can imagine, especially if you have like a 10 by 10 matrix. It's like there's a lot of different ways you could put these blocks together with a couple eigenvalues, right? So it's like, which one is it? So we need some result. And so I'm going to give you the theorem and maybe say, just briefly outline the sketch of the proof. And once I do, I'm then really going to be focused on using that theorem to give us some information in this case and recovering some facts for us. So here's the theorem. Here's the answer of how many of each size block there are. The answer is there are 2 gamma k minus gamma k plus 1 minus gamma k minus 1 blocks of the form j k lambda, where each lambda k is just equal to the nullity, the dimension of your null space, of a minus I lambda to the k. Okay. Maybe we should use this theorem, and then I'll say a few words on how to prove it. But let me just make sure we're clear on what it's saying. We're still trying to figure out what J is. And so the theorem says, if you want to know what J is, we need to calculate these guys gamma, right? For each eigenvalue, for the eigenvalue lambda equals 1, and for the eigenvalue lambda equals 2, we need to calculate these gamma values. Now, we've already calculated one of them. Gamma 1 for 1 is just the nullity of a minus lambda I, which we've already said, we already looked at this. We looked at a minus a copy of the identity. We found the nullity. That's just our geometric multiplicity, right? So gamma 1 is just geometric multiplicity. We already found that it comes out to be 1. And same thing down here. Your gamma 1 for lambda equals 2 is also just equal to 1. But if you want to figure out what gamma 2 is, what we need to do is calculate for lambda equals 1, a minus 1 times the identity, square it, and then find the degrees of freedom in your null space, the dimension of your null space. We could spend a blackboard doing that, or you could type it into Wolfram Alpha. You could be like, this matrix minus 1 times the density. You could say to the second power. You could just ask for the nullity. Wolfram Alpha would give it to you, or whatever algebraic computing system you want to use. I did this last night. It came out to be, 1. And then I kept going. I was like, what is gamma 3? He's also 1. And if you want to keep going, you can, but that's going to be enough data for us. And then here we can ask, what is gamma 2 when your eigenvalue is 2? So now you're subtracting 2 times off the identity. And it came off to be 2. And what is gamma 3? It's also 2. You just type this into Wolfram Alpha, right? So what is this formula saying? Well, if you want to know how many blocks are there of the form jk lambda, we can just, let's consider different values. Let's first do how many guys will it be, how many 1 by 1 blocks will it be for the eigenvalue 1? And you just say, well, according to the formula, it's 2 times 1 minus, okay, I haven't told you what lambda 0 is, gamma 0. So what is gamma 0? Let's come over here and think. Gamma 0, by definition, is just the nullity of what? Some matrix to the 0th power. That's the identity matrix. What's the null space of the identity matrix? Just single point, right? It's just the vector 0, 0, 0, or however many zeros you have. So the dimension of that is 0. So your gamma 0 is always 0. So my gamma 0s are always 0, regardless of the choice of matrix. So it's 1 minus 0 minus 1. So this tells me there's going to be 0 1 by 1 blocks with lambda 1. Yeah. Good, 2 times it. So now it tells me there's 1 block. Okay, very good. Thank you. Forgot about the times 2. And then you're like, well, how many 2 by 2 blocks are there? And well, it's just going to come out to be 0 now, because we've already found our block. There could be another block, but it won't be. I mean, plug this in. 2 times gamma 2, so 2 times 1 is 2, minus gamma 1, minus gamma 3 is 0, right? By way of contrast, how many 1 by 1 blocks are there with your lambda equal to 2? Well, now we do 2 times 1 minus 0 minus your gamma 2 gives you 0. So there are 0 1 by 1 blocks. But how many 2 by 2 blocks are there? 2 times 2 is 4. Minus 1 minus 2 gives me 1. So what is my matrix J? What does J look like? It's got 1 by 1 block with 1s. So there's that block. And then 1 2 by 2 block with 2s. So that 2 by 2 block should look something like 2, 2, and then a 1 up there. And 1s in the rest of this. So that's what my J looks like. So this theorem is just giving us a way to count the number of blocks. Okay. So how might you prove this? So maybe I'll just say a few quick words. So the idea of the proof. So we're really trying to, so I guess there's two key ingredients. First, you need to convince yourself when you're thinking about the nullity of some a minus lambda I, that's the same as just the nullity of you can pull out a P and P inverse. So it's just changing A to J, and there's some change of basis. And nullity is preserved under a change of basis. So this is just the nullity of J minus lambda I. So if we come back to this example, your change of basis does not preserve your eigenvectors. Your eigenvector changed from V1 to P times V1. But P is an invertible matrix. So it's going to preserve whatever, if you have some collection of vectors of dimension 3, and you multiply it by an invertible matrix, nothing gets lost, right? Nothing's getting sent to, no non-zero vectors getting sent to 0. So nothing's being collapsed away. So since P is invertible, your nullity is preserved. The dimension of your null space is preserved. The particular vectors are changed from V1 to P of V1, but the dimension is preserved. So that allows you to move from here to here. OK, so then what you just do is you just sit down and you spend 20 minutes thinking about what the nullity of J minus lambda I looks like. And you're like, oh, OK, well, depending on what your values of lambda are, you're just going to be clearing out all of those lambdas into zeros for one of those blocks, right? And then you kind of start thinking about, OK, how does that impact the nullity? And then you just think a little bit about if you do have a block that has zeros all along the diagonal and ones above it, what does that matrix look like? What's the nullity of that matrix? And it turns out if it's like a k by k matrix, it's nullity k. You do some clever counting argument. So there's some chasing there. But what you end up with at the end of the day is you get this nice formula that says that the number of blocks, well let me just rewrite it. The number of blocks of size at least k, you end up with gamma k minus j, gamma k minus 1 blocks j of size at least k. So j sub j, where j is at least k. And then from this, you can recover your original formula, right? Like, if this is the number of blocks of size at least j, then you're like, how many blocks do I have size exactly k? Well, all I need to do is I count the number of blocks where j is bigger than or equal to k plus 1, and I minus the number of blocks where j is greater than or equal to k. And so you just have this formula, gamma k plus 1 minus gamma k, because I've shifted it all by 1, minus what j is at least k, gamma k minus gamma k minus 1. And then you do some arithmetic and you recover your original formula. Oh, did I do that backwards? Yeah, I did this backwards. I want to count the number of blocks exactly size k. So I want to subtract off all the ones that are bigger than size k. And so here you get gamma k plus a copy of gamma k, so it's 2 gamma k's. Here you have your minus gamma k minus 1. Here's your minus gamma k plus 1. OK, so you can trace through that proof. That's fine. But what I want to point out in closing is we have a theorem that tells you the number of blocks you get. So it's like it's not like it's like some mystery. It's dictated to you how many blocks you have of each size. And hence, given a matrix A, there's now an algorithm that tells us how many there will be of each size. And thus, it's unique. Right? It's not like you can come up with anything else. You just follow the algorithm, and it tells you. Unique up to reordering, because it only tells me the number I have of each size. And I could always change them around, which exactly corresponds with changing the columns of P. So here's the big theorem. We're going to come back to it Wednesday. We're going to talk about some corollaries of it. We're going to try and prove the existence part of it. But at least we see the uniqueness, that every matrix A has a unique Jordan canonical form corresponding to it. And so we'll talk about the implications of that in our next lecture.